In this set of lecture notes, we're going to talk about vectors. We actually started talking a little bit about vectors in the past. If you recall, a vector is a quantity with magnitude and direction. So we talked a little bit about how to find, or how to use vectors rather, and then we talked a little bit about what exactly we mean by the word magnitude, and then we addressed direction only in one dimension. So now we're going to talk about vectors in general. So this idea applies to 1 dimension, 2 dimensions, and 3 dimensions. We're not really going to worry about 3 dimensions in this class, although later down the line we are going to bring up the 3rd dimension, but kind of separately on its own, not in conjunction with the other 2. So first of all, a vector is denoted by an arrow. We already discussed that briefly. What we didn't say is that the length of this arrow represents the magnitude of a vector, and direction obviously is denoted by direction of the arrow. So I'm going to call this vector v, just a generic capital V, and then magnitude, of course, we wrote before as just v without the vector arrow, which can be written as absolute value of v, and sometimes you'll also see it written like this, with kind of double absolute value. I'm not going to write it like this, but you may see this if you look for other resources online. So, what about direction? Well, if it's up, down, left, right, that's kind of self-explanatory. But what if we have a vector kind of like this? So direction here is going to be denoted by theta, right? Greek letter theta. I'm sure all of you guys are familiar with this, but I'm gonna write it anyway. Okay, and of course, still magnitude, right? This is the magnitude of it. Now, in this class, I'm going to only use what's called reference angles to represent direction. Although the other common way to represent angles is by using the 360 degrees and using standard orientation. So I'll tell you about that in a minute. So the way that we denote reference angles is by kind of addressing quadrant. So for example, something like this, I could say that this is 40 degrees above positive x-axis. Something like this, I could label as, let's say, 15 degrees below negative x-axis. And maybe something like this, I could do, say, 70 degrees below positive x-axis. So I'm kind of indirectly denoting which quadrant this reference angle is going to be in. And this is how I typically write it. Positive x-axis, negative x-axis, above, below, and so on. Sometimes people use north, south, east, west. You can if you'd like. That's not what I'm going to do. And I don't particularly like doing that in problem solving because it doesn't always fit into the description of the problem. But sometimes people do say something like this, right? 40 degrees north of east, or 30 degrees south of west. So you can use that once in a while, not always, only when it's appropriate for the problem. So in general, when we deal with reference angles, it's going to be an angle always between 0 and 90 degrees. And notice how I'm not including either 0 or 90. So between 0 and 90 degrees, but not equal to 0 or 90. And then we would specify the quadrant, right, in one way, shape, or form. And this is typically how you should be doing this, by using the x-axis and using the words below and above. Also, reference angle always measured with respect to x-axis. Everybody knows this abbreviation WRT stands for with respect to x-axis. So if angle is given to you in any other way, not with respect to the x-axis, in order to do everything that we're about to do with vectors, you're going to have to convert it to that notation. Make sure that it's in correct orientation or correct notation. Some other way of referring to direction would be the standard orientation. This is probably what you're used to from trig class. So standard orientation is measured counterclockwise with relation to the x-axis. So counterclockwise with respect to plus x-axis. Right, so this would be 0 degrees, 90 degrees, 180 degrees, 270 degrees, and then we're back to 360 degrees. So something like this would be, for example, 130 degrees. And then you would not specify the quadrant. It would be implied that that this angle is in standard orientation, so you would know exactly which quadrant it's in just by simply addressing the angle itself. Sometimes this is useful, and I don't mind if you use this notation in this class, but please be mindful of negative signs when we get to components in a few minutes. So everything that I'm going to show you in this lecture notes depends on using direction in terms of reference angles. There is one more method of addressing direction. This is called bearing. Okay, so bearing is measured with respect to positive y-axis. Y-axis. Okay, so we are not going to use this notation in this class, and I don't recommend even doing this on your own. This is used a lot in navigation, but other than that, navigation, flying, maybe orienteering, but nobody else uses that. So let's draw that. So from the positive axis, for example, this could be 40 degrees west, or this could be 80 degrees. Oops, sorry, this is 40 degrees east, of course, and this is 80 degrees west. You might also see it written kind of like this: north 40 degrees east, or north 80 degrees west. If you see this notation, then kind of by analogy, you could also do something like this, right? South and then 30 degrees east. So go south first, and then from south 30 degrees east. You could do that. Again, not the best way to address angles, and this method of addressing the angles is inconsistent with everything else that I'm going to show you today in terms of calculations. So in this class, I'm going to use reference angles almost exclusively. So that's how you address direction. Let's talk a little bit about vector algebra, or better yet, vector operations. So you should be able to do this vector operations using graphical representation as well as algebraic representation. So before I start drawing this, before I show you operations, let me show you another thing really quickly: vector notation. Okay, so obviously we can use this notation here. Okay, let me show you this. So we can use angle brackets to denote direction of vectors. We'll talk a little bit more about it when we get to components, but that's just so that I can address it. So basically, this notation means that you have an x contribution and a y contribution. So in order to draw this vector, what I would do is I would start at the origin and go 3 units to the right and 4 units up, and then 3 units to the right, 4 units up. I would draw something like this. So here is my vector v. Let's just practice it with one more. Let's call this vector u, -2, -1. So again, I would start with, I'd start at the origin, go 2 units to the left and 1 unit down, and draw vector u. So that's how that angle bracket notation works. So we need that to see what kinds of vector operations we can do. Okay, vector operations. We'll start with negation. So negation. Another name for negation is vector opposite. So if I write vector v like this, opposite of a vector, negative of a vector, is going to be written as just -v. Algebraically, really easy. I'm just going to keep using that vector v that I have above. So basically, I'm distributing this negative sign to both x and y part of this vector, and that's it. So really easy, right? So if I have this vector v, something like this, the opposite of vector v is going to have exactly the same magnitude and direction, but pointing in the opposite way. That's -v. So this is not particularly difficult. The next one is called scalar multiple. So scalar multiple, so let's say I again keep the same vector v, I can multiply it by a scalar. I'm going to keep reusing my vector v here. And again, this is just taking that scalar and distributing it to both x and y components. So also algebraically, that's not very difficult. Graphically, so here is my vector v. I literally just have to make it twice as long. So notice how I'm actually counting squares, right? So this is definitely easier to do if you have graph paper. So here is going to be, that's not a very straight line. Here is going to be a vector 2v. Okay. You can combine negation and scalar multiple. So for example, you could make something like -3v. So algebraically, again, I would distribute the -3 into both components, like this. So I already have my vector v. I'm just going to count squares here. Okay, so it's going to look something like this. It's much easier when you draw using a ruler or a straight edge, and of course graph paper. Okay. All right. So here is our scalar multiple. The next operation is called vector addition. So I'm going to keep using my v. And then the other vector that we had was vector u. And this was -2, -1. So if I'm going to add v plus u, algebraically, first, now I'm going to write it out like this the first time, even though it's obviously really easy, but just to bring up your attention to it. The most important thing about vector addition is to treat the x's separately and the y's separately. Let me write it out. And I'm going to write it like this. Add x and y components separately. This is going to be very important when we start talking about forces and how forces influence motion. So x and y component are always separate and independent from each other. We haven't really talked about components per se. We'll do that in just a minute. But you're already kind of seeing the patterns here, right? So you have the first term in the angle brackets, that's your x. And then the second term in the angle brackets, that's your y. So we add them separately. Okay, so here is my vector v again. And here is my vector u. So I'm going to add them. So the way I'm going to add these guys is I'm going to draw a coordinate axis, here a coordinate plane. So obviously vector v, 3 units to the right, 4 units up. And then what I'm going to do is I'm going to place the end point of a vector, of the next vector, into the beginning of the previous one, like this. That's my vector u. Now let me also tell you about a little bit more about terminology here. This is the starting point. We never actually call it that. We call it the tail end of the vector. And this here is the ending point. Again, we never refer to it that way. We call it the tip of the vector. So notice when I placed the tail of vector u onto the tip of vector v, that's how I'm representing vector addition graphically. This is called tip-to-tail method. There are other methods too. I'll show you one in a minute. But this is by far the easiest method if you have multiple vectors to add. Not just 2, but more than 2. So the way that you would draw the result of that addition is you go to the very start and you draw the vector to the ending point. So let's call this r. So r is the resultant vector. So here is how I would write that. Vector r equals v vector plus u vector. So r is the resultant. It's the result of this vector addition. Notice I always start r at the start of the first of those two vectors and end it at the end of the last vector. Okay, so that's the tip-to-tail method. Let's we'll do another example in just a second, but let's see what happens when we reverse the order of these vectors. Okay, so I'm going to this time start with u and then place the tail of vector v at the tip of vector u. So from the tip of u, I'm going to go 3 units to the right and 4 units up. Oops, that's not 4 units. And so 1, 2, 3, 4. Okay, and that's my vector v. And here is my r. And notice how I got exactly the same resultant vector as in the previous case. So it doesn't actually matter the order in which you add vectors. So in algebra, you may recall that this was called commutative property. The vectors commute, as in you can add them in any order. Okay. Now you also may have noticed that I'm kind of moving vectors around. So I need to tell you this too. Vectors don't have a definite location. You can move them as necessary for all of this algebraic or graphical purposes, you can move them as long as you preserve magnitude and direction. Notice how magnitude and direction, you can actually measure it in terms of length and angle, or you can refer to it, sort of not really, by those components, right? So as long as I keep counting the same number of squares each way, I will get the same result. So I can move vectors around. There is another method to add two vectors. This is called a parallelogram method. Okay, this is only good for two vectors. So I'm going to keep using my vectors v and u. Same two vectors as I had before. So here is how I'm going to do parallelogram method. I am going to, again, start by drawing each one of these vectors. Here is v. This time I'm going to make both vectors originate at the origin, or better, tails at the origin. And then what I'm going to do is draw a parallelogram. So draw the remaining two sides. Okay, let me delete all of these. Okay, so draw the two sides of parallelogram as parallel to the ones that we already have. Kind of like this, right? And then the resultant vector, I'll keep calling it R, is the diagonal, or I guess sort of hypotenuse of that parallelogram. Diagonal is a better word. So if you have, for example, two vectors like this, and you draw your parallelogram, it's actually not a parallelogram, it's a rectangle. And then the diagonal of that is the resultant. This is going to come in quite handy when we talk about components in a minute. So this is great. This is actually maybe a little bit simpler, but again, this only works for two vectors, whereas the tip to tail method here works for any number of vectors. And of course, it doesn't matter which of these graphical representations you use, the graphical result has to agree with the algebraic calculation that you see at the very top. So in principle, you should be able to do either or, but it's good to do both and then compare them. Okay, let's do a slightly more complicated example here. So I'm going to use different vectors now. I'll use vector A, vector B, and vector C. Okay, and what I want to calculate, I'll keep calling that R, the resultant, is 2A minus B minus 3C. So I'm combining here negation, vector addition, and scalar multiplication. Now, subtraction is really just adding of a negative, right? So I could also write it like this. You don't have to do this, but that's what we mean by subtraction, right? Addition of a negative. So we really don't ever talk about subtraction of vectors. This is how we usually represent them when we draw it graphically. So I'm going to do this algebraically first. I'm going to plug in. I'll stick with a minus sign here. I'm going to plug in all three of these vectors and make sure that I'm only dealing separately with the x's and the y's. Again, you don't have to do this. You don't have to write this intermediate step if you're okay and it feels easy to you. But I'm just gonna do that to make a point, I guess. Okay, so that's my resultant. So even when I do this algebraically or numerically, graphically, I still expect to get the same result. Okay, so let's see how this works out graphically. Much easier to do with a ruler, of course. Barely. Okay, so I'm gonna start with my vector 2a. So a was 1, 5, so 2a, I'm gonna go 2 units to the right and 10 units up. So here is my vector 2a. Okay, and then my vector negative b, so I'm gonna put the tail of that to the tip of this previous one. So negative b is going to be 2, negative 4. So from the tip of 2a, right, 1, 2 to the right, and then 1, 2, 3, 4 down, like this. Okay. Okay, and then from that point, negative 3c. So now 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's my negative 3c. See how it doesn't have a y component to it? So this was negative b, and this was negative 3c. And then from the tip of the very first one to the, from the tail of the very first one to the tip of the last one. Here is our resultant. And then check to make sure that it agrees with our calculation. So it should be 13 units to the right from the starting point. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Bingo. And then 6 units up. 4, 5, 6. Bingo. Okay. So this is why this tip to tail method is so user-friendly, because you can do you can add as many vectors as you need to this way, and also perform negation, scalar multiple, kind of all at once. Okay. The next thing that we need to learn is vector components. So I already used this word, but let's see how this works in a little bit more details. Vector components. So let me bring up my vector v again. Okay. And then we said that this was the x component, and this is the y component. So the word components literally means the contribution to the vector from its horizontal piece and its vertical piece. So the contribution to its horizontal piece, or from its horizontal piece, is 3 units horizontally. And then, of course, vertical piece would be 4 units vertically. And this is how you draw that vector. So we kind of already know that. Now, there is another way of representing the same thing. So instead of writing angle brackets, sometimes people use what's called IJK notation. In fact, it really should be written like this: I hat, J hat, and K hat. And it literally means the same thing. So this guy's here, the IJK, or I hat, J hat, I hat, J hat, K hat. These are called unit vectors. Now the word unit actually represents length equals 1, like a unit circle, right? In unit circle, radius is 1. Now it doesn't actually have anything to do with units. It has to do with unity, as in 1. Oh, and by the way, everything that I've done so far, I've been writing this without units, and that's fine. So for now, we're just learning vector operations, so we don't have to worry about units. Once we start applying vectors to physical quantities, then obviously we're going to need to worry about that. And we kind of already did that a little bit when we talked about position, velocity, acceleration, and all of that stuff. Going back to this, so unit vectors means length equals to 1. So the same vector v, in terms of ijk notation, could be written like this: 3i hat plus 4j hat. And it means exactly the same thing. So this just kind of brings out the fact that you have a contribution of 3 units in the horizontal directions and 4 units in the vertical direction. So ijk, well, right now I'm not going to worry about k. I hat, actually, let me draw it like this. If I had a coordinate system, I hat is a vector that has unit 1 in the x direction, and j hat is the vector that has unit 1 in the y direction. Okay, k would have to deal with z. Let's not worry about that just yet. So for now, we're just talking about 2D stuff, right? Vectors in 2 dimensions. So we'll deal with k later. Okay, so again, it kind of looks goofy, but this is all there is to it. Now, if you wanted to stick units onto it, like let's say you had velocity, you could write 3i plus 4j and then put meters per second on the end. Or you could write 3 meters per second I hat plus 4 meters per second j hat. Or you could write it like this: 3, 4, and then put meters per second after. Or you could put 3 meters per second, comma, 4 meters per second. So if you had 2-dimensional motion, for example, velocity vector, you would obviously have to indicate units, right? And then you could use either one of these 2 notations, either the angle brackets or the ijk notation, ij notation, to represent, again, the contributions to the vector from the horizontal direction and the vertical direction. If it's that easy, why do we care? Well, for one thing, we can get magnitude and direction from components. Now remember, the length here, the length of this vector, that's the magnitude, right? And this angle theta is the direction. So think about this as basically either a rectangle or a triangle. So I can do 3 units in the x direction and 4 units in the y direction, right? And this is my vector v. So the horizontal piece I can call vx. And the vertical piece I can call vy. Now for components, it's actually not super essential that you put vector arrows on it, but I guess I usually do. Like this. Okay. Now if you're thinking in terms of what you know about triangles, then you can write v, the magnitude, right? V squared is equal to vx squared plus vy squared. That's just your regular garden variety Pythagorean theorem. Except I'm not going to write it like this. I'm going to write magnitude v is equal to square root of vx squared plus vy squared. So if you know components of a vector, you can easily figure out its magnitude. For example, that vector v that we've been using, I could do square root of 3 squared plus 4 squared, which will give me 5. So the length of that vector v is 5, whatever units. Okay? Also going back to my triangle here, I could write tangent theta equals the opposite side over the adjacent side. That's also fairly easy. Except I'm also not going to write that as a final direction. I'm going to write theta equals inverse tangent of the y component over the x component. I'm going to box this. So again, for our example, theta is inverse tangent of 4/3. And then, of course, you would plug it into your calculator. Make sure that your calculator is in degree mode. We're not going to need anything in radian in this class. And I get 53.1 degrees. Okay, so this theta here, okay, so magnitude we figured out was 5, and the theta was 53.1 degrees. So that's what that means. Now you have to be really careful with inverse tangent, okay, because inverse tangent only gives angles that are between -90 degrees and +90 degrees. And sometimes that's just not appropriate. Like, for example, we had the vector u that was -2, -1. So if you found theta, if you found the direction of that by doing the y component over the x component, you plugged it into your calculator would give you positive 26.6 degrees. But that's clearly not correct. This vector u is in the third quadrant, right? So what you're getting here is reference angle of 26.6 degrees. So then you would give the answer as 26.6 degrees below negative x-axis. Okay, and that would be your answer for that. So my recommendation for when you're dealing with inverse tangent, just don't even worry about the negative signs on components. Drop the negative signs and then just calculate the angle, and then based on which quadrant that vector is located at, you can name the angle properly using reference angles, using the words x-axis and then above, below, and so on. So just be very careful with inverse tangent. Okay. Last thing to show you is how to calculate components from magnitude and direction. Oops, calculation of components. So again, I'm going to draw my vector here, sticking with the same vector. Okay, so this time, let's say that I know that magnitude is 5, and that whatever the angle is, 53.1 degrees, right? So this time, I would give you magnitude and direction, and I would tell you where that vector is, right? So I would say something like 53.1 degrees above positive x-axis, and I could ask you for components. So this is called calculation of components, or resolving vector into components. Resolving vector into components. So I can do this graphically. So here is my vector v. The way that I do it graphically is I basically draw a rectangle around this vector, like this, where the vector itself is the diagonal of that rectangle. Remember, I showed you the rectangle a little while ago? And I'm drawing this rectangle in such a way that 2 of the sides are horizontal and 2 of the sides are vertical. And then I'm going to draw the x component like this, and the y component like this. And this, of course, is my original v. So I can draw it as a triangle, like so. In both cases, this is theta. In both cases, the original vector is either the diagonal or the hypotenuse, right? So I can either draw it as a triangle or as a rectangle. That's entirely up to you. Both types of drawings have their benefits. So for example, for now, while we're just dealing with vectors, it's probably easier to draw triangles. But when we start applying these vectors to something like force addition, then drawing that rectangle where the components are the two sides, that's a little bit more beneficial. And you'll see why when we get to that. Okay, so again, let's just stick with that triangle that I have there. So from that triangle, I could write cosine theta is equal to Vx over V, and sine theta is equal to Vy over V. Notice that I'm writing V here as a magnitude, not as a vector, right? Because all I'm doing is literally just writing adjacent side over hypotenuse or opposite side over hypotenuse. Well, if I rearrange those two equations a little bit, Vx is going to be V cosine theta, and Vy is going to be V sine theta. Like this. Okay. So you should be able to go both ways now, right? You can calculate magnitude and direction from components, or you can calculate both components from magnitude and direction. And the most important thing for both of this actually is to remember the negative signs, right? So positive and up, excuse me, to the right and up is positive, and to the left and down is negative, right? And then of course we measure reference angles with respect to the x-axis. So as long as you keep that in mind and you keep all your minus signs consistent with all of these calculations, that's literally all it takes. None of this calculation stuff for vectors is really difficult. You just really have to be consistent with all the minus signs.